Alright, so this is chapter 3, section 3. We're going to go over the unit circle and how that applies to our linear functions, or circular functions, not linear functions. Alright, so we're going to find the value of the circular functions, and we're going to find the lengths of line segments towards the end of the lecture here, okay? So, what's the point of the unit circle? The unit circle, alright, has a center at 0, 0, and a radius of 1. So that no matter where we are on the circle, alright, the radius will always be 1 for all of our calculations here. And we're going to apply everything in terms of sine and cosine, where we're going to have our two components, our horizontal component, which is in terms of cosine, and our vertical component, which is in terms of sine. Alright, all kind of based on our arc length. So how we're going to find all these, came about from the very important triangles that we found before in chapter 2, our 30, 60, 90 triangles and our 45, 45, 90 triangles, all right, otherwise known as our square root of 3, our 1 square root of 3 2 triangle, and our 1 square root of 2 triangle in that respect, okay? So we are going to find all the values, okay, as we go around the circle holding the radius at 1, okay? So the point is, anywhere we go on this circle, our magnitude will always be held at 1 when we do this, okay? When we interpret these, okay, we call them circular functions. Remember a circular function, right? We got x squared plus y squared equals 1. That's the definition really of how we draw a circle too, if you remember from your conics section in Algebra 2. Alright, so if we take a look at this, alright, S is a real number, okay, and we're talking about the arc length on the unit circle. Okay, so sine of S equals y, cosine of S equals x, and tangent of S equals y over x. That's really nothing new, right? I've told you all along that we see x as a horizontal component as well as cosine, and y and sine are a vertical component. And then obviously the other trig functions are just inverses of one another. So nothing really new here, all right? The unit circle, all right? We spent a lot of time in chapter 2 when we did reference angles and found all these specific locations at these specific angles, right? We would draw a circle to 120 degrees, or an arc length, or an arc radius, okay, length, an angle to 120 degrees. And then we would drop a reference angle and find the values at those specific locations, okay, and how we're able to do that. So just to pull out a particular example, if we look at 120 degrees, right, as if we made that our angle theta, and then we had a reference angle, our reference angle was 60, okay, and we knew that across from the 60 degrees would be the square root of 3, that the adjacent side would be -1, that would be across from the 30 degrees, and that the hypotenuse, or the magnitude, was 2. So that's why at the point location of 120 degrees, all right, sine, which is the y component, is square root of 3 over 2. Then cosine is -1 over 2. That's the x component. So if we look around the outside of the unit circle, that's an xy coordinate. So looking back at 120 degrees there, -1/2 comma square root of 3 over 2, that's the x and y location, right? And those were found using SOHCAHTOA and reference angles. So this really shouldn't be a whole lot of news to us how we can come up with those values on the unit circle here. Everything is tied to 30, 45, 60, all right, in each quadrant. So in quadrant 1, all right, those are the angles, 30, 45, 60. In quadrant 2, they're the reference angles, where the reference angles are 60, 45, and 30. Same with quadrant 3 and quadrant 4. Those are all based on the reference angles that we did in chapter 2. Okay, so the unit circle, right, it's symmetric with respect to the x and y axis and the origin. So if point A in AB lies on the unit circle, so do all the other following points. A and -B, -A and B, and -A, -B, right? All the inverse and opposites. Those are really just all the opposites, okay? Because, why? Because they're all equidistant from the origin. So that's why all of those will work, okay? For a point on the unit circle, okay, we use the reference arc, to do the calculation. Okay, so in quadrant 1, remember, those are the angles that we're dealing with. We're dealing with 30, 60, 45, or we're dealing with what? Pi over 6, pi over 4, and pi over 3. And those are all determined by drawing the reference angles for each one of those. Okay, so it's really the arc length, right? S equals r theta. But we have the points that were all given to us that we calculated using right triangle trig when we use the reference angle and draw the perpendicular. Okay, so cosine of S, cosine, and sine of S. Okay, that's really how we write this out here. So we know that S is pi over 3. That's the angle, right? Pi over 3 is also 60 degrees. So cosine of pi over 3 is equal to 1/2 when we write that out, right? Or we said cosine of 60 is equal to 1/2, right? Because the adjacent side was 1, the hypotenuse was 2, and it's all based on the unit circle when we go through this. So a lot of this is kind of reviewing stuff that we did at the beginning of chapter 2, using reference angles in each quadrant, and we're just doing it with the unit circle though, so the radius is 1. Okay, so we've already reviewed this as well, so this is no news. We're just going to be applying stuff here. The Pythagorean identity, right? Very important one. We touched on this in chapter 2 as well. When we were solving using trig identities instead, right? We'd substitute in like a cosine value to get the sine value or vice versa. All right, so sine squared plus cosine squared is equal to 1, where S is just representing the arc length based on the particular given angle that we calculated. Okay, same when we started talking about ranges last in unit 2, right? Now we're going to talk about the domains, the x values. Sine and cosine are infinite. They go on forever. They go from negative infinity to positive infinity. Remember, tangent will not, right? Remember, we covered that because tangent is really what? Sine over cosine. Anytime cosine was equal to 0, we created an asymptote in the tangent graph, all right? It was undefined. We had division by 0. That's why secant also isn't from negative infinity to positive infinity, because secant is 1 over cosine. So anytime cosine went to 0, secant's going to have an asymptote. All right? Cotangent is what? Cosine over sine. So anytime sine goes to 0, cotangent's going to have an asymptote. Anytime that cosecant, remember cosecant is 1 over sine. Anytime cosecant goes to, or sine goes to 0, okay, cosecant will have an asymptote because division by 0. So remember, when we're discussing this, this is all about the x values. We're talking domain. We talked about range before with in chapter 2, and you know, like sine and cosine would go between -1 and +1. Okay, and tangent was negative infinity, positive infinity. This is the range. This is the x values on it. Okay. So if we want to evaluate a circular function, we're actually getting, you know, the real values based on the theta. The one thing that you need to make sure that you're doing is when we do this, that your calculators are going to be in radian mode. The circular functions we're dealing with, we are going to deal with strictly in kind of radians in this sense, all right? So we got to make sure that we know pi over 3, pi over 4, pi over 6, okay, pi over 2, what all those mean and where the locations are on the unit circle. Okay, but make sure our calculators are in the radians mode. We did all of this with degrees before, right? I told you, hey, what's sine of 60 in your calculator? And we had the calculator in degree mode. Now you're going to find the values, okay? We can use them in the calculator, or we can draw them out, and all those different aspects. But what we need to know is what? What is 3 pi over 2? 3 pi over 2 is equivalent to what? 270 degrees. So for us, you know, it's graphed out right here in blue. That's the location 0, -1. So it's really just recalling, hey, sine of 3 pi over 2 is the same as sine of 270. So what's the value there? It's going to be -1. What's the cosine there? 0. We're just looking at the unit circle here. I'm just interpreting the graph. I haven't even plugged anything into the calculator yet. And tangent's going to be what? Sine over cosine, or -1 over 0. So is tangent even defined there? No. Okay, so you should be able to mentally analyze some of these once we get to know them. Okay? So we should know that 0 is the x value, -1 is the y value when we are looking at 3 pi over 2. Okay? So when we rewrite this, we know that sine of s is equal to y. So we know, okay, sine of 3 pi over 2 is -1. We know cosine of 3 pi over 2 is 0. And since tangent is y over s, -1 over 0 is 0. So we are undefined tangent there. Okay, does that make sense? That's the exact same way that we evaluated sine of 270 degrees, right, in previous chapters. Alright, so we want to use this figure, right? What is this figure? This is the unit circle. If I were you in your notes, I would make sure that you write out the unit circle. We may have a quiz where you have to actually fill in all the different values. You need to know all the points, you need to know all the degrees, and you need to know all of the radians portions of this. So what we want to do, let's figure out the exact values of sine of 7 pi over 4 and sine of 7 pi over 4. Alright, so first of all, we got to find where is 7 pi over 4 at on the chart. Okay, if we look, and we'll go through this, we've gone through it on the board. Alright, those of you guys at home, you got to be able to interpret this piece, alright? We got 7 pi over 4 is where? It's in the 4th quadrant. And if we look, what are the coordinates? The x coordinate is square root of 2 over 2. The y coordinate is negative square root of 2 over 2. Does that make sense? Remember, all students take calculus. So calculus, the cosine value or the x value has to be positive there. And the sine value, the y value, has to be negative there. Alright, so if we interpret this, we should know and be like, oh, cosine 7 pi over 4, it's the x value, it's square root of 2 over 2. Oh, sine of 7 pi over 4, it's the y value, it's going to be negative square root of 2 over 2. Alright, literally we're just reading the chart here and understanding what the actual values are at those particular radian values. Okay, so it corresponds to that location on the unit circle. All right, and if you struggle with the radian piece because you don't have the unit circle in front of you, take that angle, take 7 pi over 4, put it into degrees, right? Multiply by 180 over pi. Put it into degrees and it'll tell you what degree that is so that you'll know what angle to look for and what quadrant to be in so that you can apply the all students take calculus and know if you should be positive or negative and that sort of thing. Alright, but literally it's just kind of interpreting this chart here. So let's look at this one. We want to use the figure to determine tangent of -5 pi over 3. Alright, so the first thing that we've got to do is figure out what quadrant is 5 pi over 3 in. Okay, 5 pi over 3 is in what? The 4th quadrant. Okay, we look for the positive value. Why is it negative? Because tangent's negative in the 4th quadrant. But 5 pi over 3 is in the 4th quadrant. And we look at the coordinate next to it, it says x is 1/2, y is negative square root of 3 over 2. So, tangent is going to be what? Opposite over adjacent, so it's going to be the y over the x. It's going to be negative square root of 3 over 2 divided by 1/2, which ends up giving us, okay, negative square root of 3. Hopefully that makes sense, right? We have square root of 3 over 2 divided by 1/2. When we divide by a fraction, we multiply by the reciprocal. So the 2's cancel. We're left with square root of 3 over 1, all right, which is just the square root of 3. So I do expect you guys to make sure that you understand how to do those math. But just remember, when we divide fractions like we're doing in this example, we take the second one and we multiply by the reciprocal to get our solution. Okay. So using reference angles, another thing, we're looking back at what we did in chapter 2 with everything. So in this case, we want to find what we're going to call the exact value of cosine of 2 pi over 3. So first of all, we got to remember what quadrant does that go into. So something that you might want to do, put it in degrees just so that you get a frame of reference, all right? You may not remember in radians where everything goes, but if you put it into degrees, okay, by multiplying by pi over 180, we're going to be multiplying by 180 over pi, so we should get what? When we simplify that down, 180 divided by 3 is 60, 60 times 2 is 120, and the pi's cancel. So we know it's 120 degrees, so we are in the second quadrant, all right? And we know that the reference angle has to be 180 minus 120, which is 60. Then in your mind, hey, what is 60 degrees in radians? Because if you know what 45, 30, and 60 degrees is in radians, you'll be much more successful through all of this, okay? But we're looking for what is 60 degrees in radians. Okay, it's pi over 3, so we're going to do that. Okay, so I would make sure, mentally that it gives you a good frame of reference to do this. So we know, all right, at 60 degrees, if we go back and look at the unit circle, we can see that we're at 1/2, right? And why is it negative? Because cosine is negative in the second quadrant. So that's why we end up with negative 1 over 2. Just the reference angle there, we're using 60 degrees. Okay, we're using a 1 square root of 3, 2 triangle. Okay, and the adjacent side is the negative 1. Okay, and the magnitude is 2, so that's why it's negative 1/2. So very simple if we can convert it to degrees, or just to give us a good frame of reference in our mind. So now let's find calculator approximations. Remember, when we see them as decimals like this, I want you to make sure that you're thinking of radians. All right, so we want to find the calculator approximation for each one of these. First thing that you need to do is make sure your calculator is in radians mode. So make sure that you hit mode, go down to radians, hit over and hit enter. Make sure it's in radian modes. Now it's pretty straightforward from here. You're going to hit cosine of 1.85 in your calculator and hit enter. You should be getting negative 0.275. Now, if you're not getting that, that means that you did something and forgot to put it into radians mode instead of degree. You guys should be able to do the next one, cosine of 0.5149. Okay, make sure you pause the video, make sure that you're getting the exact answers here, okay? Same with these. Now, what are these? These ones are a little bit more scary, right? Because they're inverse functions and we don't have a cotangent button on our calculator or a secant button. So we know that we have to use, with cotangent, we got to do something with the tangent function, and with secant, we have to do something with the cosine function when we do this, okay? So when we're going to calculate or approximate this, when we have to use cotangent, we're going to take 1 divided by tangent of whatever that angle is. 1 divided by tangent of that angle. Okay, it'll give us the inverse ratio. So when we take 1 divided by tangent of 1.32, you should get 0.255. So secant, what do you think you're going to do? You're going to take 1 divided by cosine of that value. Okay, and you're going to get negative 1.02. So that's the ratio piece, okay? Not everything's going to work out nicely in radians in form of 1 square root of 2 triangles or square root of 3 2 triangles for us, okay? So making sure that we are in radians, okay? Very, very important. So we want to find the approximate value of S on the interval 0 to pi over 2 if cosine of S is 0.9685. All right, so in this case, we got to remember how to go the opposite direction, okay? The previous example, okay, you were given S and you had to use the calculator and you got 0.9685. Now we're going the other direction. We actually have to find S. So when we go the other direction, we're using inverse cosine. So for you, that means hitting second cosine of 0.9685. So this is when we're looking for S, or we're looking for that angle, right? We're going to use cosine inverse. So you're going to use cosine inverse, second cosine of 0.9685. Make sure you do this on your calculator. You should be getting 0.2517 remember that your calculator in this scenario needs to be in radians mode. Okay? Here you can check yourself. If you type in cosine of 0.2517, you should get 0.9685. So it's a good way to kind of check, make sure you're doing it. All right, let's do this one. We want to find the exact value of S. We want to be on the specific interval from pi to 3 pi over 2. What quadrant is that in? That's in quadrant 3. We've got to be very, very important. Should our answer be positive or negative here? I want you to think about that. All students take calculus. Should tangent be positive in quadrant 3? I think so, right? And it is. It's a positive one. So in this case, we're just going to do what? Tangent inverse. You're going to hit second tangent. Okay, in this case, 1. And you're going to get 0.78. Now, why do we have to add pi? This is the part everybody will screw up. Okay, we're adding pi because we're 100. When we do tangent inverse of 1, that puts us in the first quadrant. That does not put us in the third quadrant. So when you do tangent inverse of 1, you got to be careful. We need to end up in the third quadrant. How far apart is the first quadrant from the third quadrant? 180 degrees or pi. So we have to take our answer and add pi. When we do that, then we will end up in the third quadrant like we want. Because remember that that answer will exist in multiple quadrants. So you got to be careful when we're doing that. Be very careful when we do that. All right. So if we did it in radians, right, we know that it's pi over 4 is 0.78. So we add pi to that, so we get 5 pi over 4. Okay. All right, let's talk about something, modeling some real-world application here. We have the angle of elevation, so we talked about that in a previous chapter. All right, remember we had angle of depression and angle of elevation. All right, so in this scenario, make sure that you have this equation down in your notes so that you have it for when we take a test. All right, the angle of elevation of theta of the sun in the sky at any latitude, remember that is fat, we're going around the earth, we did that in the last chapter a little bit, is calculated with this specific formula. Because remember, the sun, it's cyclical, right? We know the seasons, we know how long it takes for us to orbit around the sun, and all those sort of things. So we can use a formula, sine of theta is equal to cosine of d, cosine of L, cosine of omega, okay, that's a little omega, don't call it W, plus sine of d, sine of L. All right, so we kind of explain what everything is here. All right, theta is 0. That's our sunrise. Okay, sunrise is when theta is 0. Okay, when theta is pi over 2, that's 90 degrees. That's going to be when the sun is directly overhead. Okay, and omega is the number of radians that the Earth has rotated through since noon. Since noon. Okay, so d is the declination of the sun, which varies because we are what? Tilted on our axis. So how the sun, when a declination, we're talking about the sunset and where it occurs. Okay, so we have this entire formula. So you might have to pause the video, write it down. Okay, and then we're going to work through it here. So Sacramento, California has a latitude of 38.5 degrees or 0.672 radians. Okay, we want to find the angle of elevation of theta of the sun at 3 p.m. on February 29th, 2012, where at that time our declination, okay, is 0.1425, and our omega, how far we moved past noon, is 0.7854. Okay, so we're going to substitute in, right? We have d, we have L, we have omega. So we're going to substitute in all those values. Okay, when we do that, all right, you can see the number we get there. You should be able to put that in your calculator. We're going to get 0.459. That means that sine of theta is 0.4593. That does not tell us what theta is. That tells us what sine of theta is. Okay, so the next step, right, we have to do sine inverse of that value. Sine inverse of that value. Okay, that gives us 0.477. That's theta. Theta is that answer. Okay, Then we have to take that and multiply it by pi or 180 over pi so that we are in radians. Okay, does that make sense? Or not radians, 180 over pi, we're putting it back to degrees. I'm sorry about that. We're multiplying by 180 over pi because we want to end up in degrees. Okay, so that's why we're doing all that. So it ends up being at 27 degrees. Okay, so that's the angle of elevation of the sun is 27.3 degrees, or 0.4773 radians. All right, last part of the section here. We want to express function value lengths of line segments. Okay, so you might want to copy this illustration down. There's going to be a few homework problems where I ask you to find a specific line segment. Let's see what we recognize here. Right, there's some right triangles going on. And then what's that blue line represent? That's our unit circle arc length right there. Okay, how do I know it's the unit circle? Because point R is 1, 0 and point S is 0, 1. That's telling me that the point OP is what? The radius of the circle, which is 1. Same with OS and OR. So the radius of our circle here is 1, and we're going to use it to apply to find different line segments using our trig function. So if we want to find the arc, right, the arc for our unit circle is SR here. Okay? So what we're really going to do is our trig functions, our 6 trig functions, okay, we can interpret them as lengths of line segments here. Alright, so how does that really work? So for cosine of theta and sine of theta, we're going to use the specific right triangle POQ. Alright, so POQ. If you look on the graph, it's nicely marked with theta for us. Alright, so we have our different right triangle trig that we can apply there, right? That's a right angle. So we know that cosine of theta is adjacent over hypotenuse. Adjacent, right, at that particular point is OQ, right? And then the hypotenuse is OP. We already know that OP is 1 because it's the unit circle. So we know in this case to find OQ, right, cosine of theta is OQ. Does that make sense, hopefully? It's the horizontal component, all right, of our unit circle. If you go back and look at the unit circle stuff we did at the beginning of the lecture, hopefully that makes sense. It's really OQ. Cosine of theta is literally just our x component of the location P. Okay? Look at sine now. Okay, sine of theta is what? PQ over OP. We know that OP is 1 because of the unit circle. So sine of theta is just PQ. That's our vertical piece at point P. This is just kind of like all the stuff we did going around the unit circle and using our reference angles. Okay? Just knowing that sine is our y, cosine is our x. So let's take a look at tangent of theta and secant of theta here. Okay? We're going to use the triangle VOR. VOR. Okay, so we're going to use the right triangle trig here. So tangent of theta is going to be what? VR over OR. VR over OR. We know that what? OR is 1 because it's on the unit circle. So we know that tangent of theta is equivalent to VR. Okay? If we want to find secant of theta, secant of theta is what? Hypotenuse over adjacent. Okay, hypotenuse over adjacent. Remember, secant's the inverse of cosine. So in this case, it's OV over OR, which is just OV over 1 because OR is on the unit circle. So secant of theta is OV. Alright, so we can do the same thing with cosecant and cotangent. I don't think I need to, re-explain those. You can see where those are developed just like we looked at the other ones. We're just using larger triangles to help do that. Okay, so what's the point of this? This is for us to solve different segment lengths, okay, using our trig functions. Okay. So there's a nice little chart here on the next page. All right, make sure that you have this all in your notes, because when you do your homework or your test, you're just going to be able to reference this. You only have to draw this once. Don't draw this each time. But notice in this one, it's nicely highlighted in blue what segment value you're going to find and what trig function will help you find that specified segment distance. Okay, so in the next example, we're literally just going to pick off here the one we need and apply it, all relative to the same theta. Alright, so you can do this in buildings if you're an architect or engineering and design or things like that, or surveying, civil engineering, all kinds of different things where this can come in handy. Alright, so let's take a look here. Suppose that angle TVU. So just to recall, the middle letter, okay, the middle letter is the angle. Okay, so V is the angle here. And it says find the exact lengths of segments OQ, PQ, VR, OV, OU, and US. Alright, well, we have to look at two things here. Notice that the line, or the ray SU, is parallel to the ray OS. That tells me that OU is a transversal. Alright, so, and we have SO and TR as parallel lines. So essentially, alright, TVU and SOV, or SOU, whichever one you want to call it, okay, they're corresponding angles. So we should know that that part is 60 degrees. So, do we use 60? No, we have to use 30. 30 is the theta. So I know that SOU is 60 degrees because it's a corresponding to our given angle of TVU. So I have to find theta, and I know that's a 90-degree angle, so 90 minus 60 is 30. So my theta is 30. Now all I have to do is go back to the chart on the previous slide and put in all my solutions. Okay, so OQ is cosine of 30, PQ is sine of 30, VR is tangent of 30. Okay, these all come off the unit circle, okay, and off the table that we just had there before. So I can do all these calculations now using a 30, 60, 90 triangle, because theta is 30. Alright, and that's just how I'm going to apply it. When I know that theta is 30 degrees, I now know all the 6 trig functions because I know the unit circle. And that's really where these values are, right? Cosine of 30 degrees off the unit circle, okay, is square root of 3 over 2. Sine of 30 degrees off the unit circle is 1/2. Go back and look at your unit circle chart. That's where all these values are coming up from. And then when we need to find secant, cosecant, and cotangent, we're just taking the inverse of cosine, sine, and tangent to get those. Okay, very, very simple. I think you guys can figure that one out. The hardest part to this problem is finding out what theta is and understanding the relationship between the other angles. Literally like stuff we did in chapter 1, right? Remember, 2 parallel lines cut by a transversal. We had to revisit the angle relationships and how those affected everything. That's it for this section. Okay, remember to email me if you guys have questions about anything. Alright, but that's just a recap of the unit circle, and we'll see you guys in class. Make sure that you have the unit circle all written out so that you have a reference for it when you take a test in here. Okay?